All right. So I'm just going to continue off where I stopped yesterday. So we are still in lecture 4, or lecture 3, I guess, optimality. And we're about to touch on this fourth subtopic, which was beyond 1 over square root t, or 1 over epsilon squared if you prefer, in high dimension. Right, so quick recap of what we saw so far. We saw that gradient descent or stochastic gradient descent, they go at a rate 1 over epsilon squared. We saw that this 1 over epsilon squared is optimal in the stochastic setting even in dimension 1. There's just nothing you can do to beat this 1 over epsilon squared when you have noise, even in low dimension. And we saw that the 1 over epsilon squared for gradient descent is optimal, at least in high dimension. So if the dimension is very, very high, then you cannot beat 1 over epsilon squared. And we saw that if the dimension was small, then you can, or smallish, then you can actually beat gradient descent. You can do something like those cutting plane methods, like the center of gravity, which goes at a rate exponential in t. Okay, exponential in the number of steps. So the rate was n log 1 over epsilon. So the question we want to ask now is, can we go beyond these obstacles of 1 over square root t, even in the high dimensional case? And as I have been alluding to several times in the class, the way to go around those lower bounds is simply going to be to make more assumptions about the functions. Okay? And one very natural assumption is strong convexity. So there are two natural assumptions, strong convexity and smoothness, and I'm going to discuss both. So the first one is strong convexity. Okay? Which is the same thing as curvature in the function. Okay, so the definition goes like this. So definition, f is alpha strongly convex if f of x can be written as g of x plus alpha over 2 norm, Euclidean norm of x squared, where g is convex. Okay, so, or another way to phrase it is f minus alpha over 2 times the norm of x squared is convex. Okay, so that's the definition. So you know that when we have been talking about least squares or logistic regression, we had the convex problem. And now what I'm saying is that if you add regularization, if you add this plus alpha norm, Euclidean norm of x squared, then you get a problem which is alpha strongly convex. And that will be very good for optimization. I will explain why. So this is equivalent. I won't prove the equivalence. It's just a couple of lines. You can do it as an exercise. This is equivalent to strengthening of the gradient inequality. So what was the gradient inequality? It was f of x minus f of y is smaller than grad f of x inner product with x minus y. We have used this inequality many times. This is just the fact that the function f is above its tangent. But now when you're strongly convex, you're not only above the tangent, but in fact you're above a quadratic which curves as alpha, okay? Whose lower curvature is alpha. So what does that mean? That means I get this is smaller than this minus alpha over 2 norm of x minus y squared. Okay, so the picture is like this. I don't know, something like that. So this is a tangent, and now so without this, I just have this inequality that the convex function is above the tangent, but now I'm saying it's in fact above a function which is a quadratic function. Okay, maybe like this. Okay, so this is this function. So you see that it has to curve. Okay, it's not only, it cannot be flat, it has to curve the function. Okay, very good. So let's see what kind of rate we can expect from this. So again, from a machine learning perspective, it's very natural. From an optimization perspective, it's good because of these things that I already said several times. if you're far from the optimum, when you have curvature, it means that your gradient is big. So you're going to have a big derivative pointing towards the optimum, and you're going to make a lot of progress. Okay. So let's do the analysis of gradient descent. Let's do the continuous time analysis. Okay, so analysis of gradient flow. So recall, how do we analyze the gradient flow? The gradient flow is that d over dt of x of t is minus grad f of xt. Okay, so this is just the trajectory of my algorithm. I denote r of t, let's say r squared of t is the distance to the optimum. So x of t minus x star squared. And I also denote delta of t to be the difference in function value. F of xt, x of t minus f of x star. Okay, these are just definitions. Now, you remember the whole point is that we want to analyze gradient descent by looking at how quickly we get to the optimum. So we're going to look at the time derivative of r squared of t. Maybe I put a 1/2 so that it's a bit nicer. So, okay, so calculation. Now it's not a definition anymore. So I do d over dt of r squared of t. What do I get? Okay, I differentiate the square. So you remember, I just open it up. I will get a 2, which cancels with that 2. Then I get the time derivative of this, inner product with this. The time derivative of this is minus grad f. So I get that this is equal to minus grad f of xt, inner product with xt minus x star. Right? And you remember what we used before was just that this thing is lower bounded by your gap to optimum. Okay, so this is smaller than minus delta t. That's just convexity. Right, just because f of xt minus f of x star is smaller, it is, I want to say, it is smaller. Why is it smaller? Minus grad f. Right. F of xt minus f of x star is smaller than this. So minus this is bigger than that. Okay, good. Okay, but now we have more because by alpha strong convexity, we have this other term. We have an additional term. So by alpha strong convexity, we have minus delta t minus alpha over 2, the norm of x minus y squared. So x minus y is x of t minus x star. L2 norm squared. Okay? So you see, you have something very nice. This thing is just alpha over 2. Not even alpha over 2, it's just alpha r of t, r squared of t. So we get that the rate at which r squared of t is decreasing is controlled by itself. Okay? And you know this OD is just the exponential. Right? So we get, again, d over dt of r squared of t is smaller. If I just drop the first term, the suboptimality gap, I just get minus alpha r squared of t, which implies that r squared of t is smaller than r squared at time 0 times e to the minus alpha t. Right, so you see, you get this exponential convergence, okay, of the gradient flow. So the gradient flow in times 1 over alpha, it's basically at the optimum. Okay, so gradient flow gets to opt in time I will write it as O tilde. Okay, so when I write a tilde, it means that I hide some logarithmic factors. Everything will be made precise eventually, but it's just for the intuition right now. 1 over alpha. Okay, just by comparison, let me compare with the old approach. By comparison, without strong convexity, what did we have? So without strong convexity, we did this trick to analyze the average of the deltas. So we had 1 over tau, the average of the delta t dt from 0 to tau. This is smaller than r0 squared, r squared at time 0 over tau. Okay, so, and you see, so that's an upper bound on the average. So gradient flow on just a convex function, it needs a time which is like, 1 over epsilon instead of log. Okay. Maybe I write it like this. Let me remove this. Let me say like this, log r0 squared over epsilon. Okay, here, time has to be of order r1 squared 0 over epsilon. Okay, so you get this exponential improvement. All right, but this is only one part of the problem because there is a discretization. Okay, so you remember now from gradient flow to gradient descent, discretization, error. Okay, I have this discretization error, which is, we wrote it last time, eta L squared. Okay, eta is your step size. So you get eta L squared error from gradient flow at time tau, which is t eta. Okay, so you do t steps of gradient descent with step size eta. So you're roughly at continuous time capital T times eta, but the error that you make is eta times L squared. Okay, this is just by the Lipschitzness. This is just assuming that the function is Lipschitz. Okay, so you remember here, what does it give? So for convex we got this trade-off, r squared 0 over t eta plus eta L squared. So that's like r0 L over square root t, okay, by optimizing over eta. Now, what is it that we get here? Here we get r squared 0 e to the minus alpha t. T is t eta plus eta L squared. So what should I take eta to be? Eta should be O tilde of 1 over alpha t. Okay, so eta should be O tilde of 1 over alpha t, which implies a O tilde of L squared over alpha t rate. Okay, maybe. Right, you see, okay, I get this exponential term. I want this exponential term to be small. For it to be small, I certainly need eta to be bigger than 1 over alpha t, because otherwise this is a constant. And if I go just a little bit above 1 over alpha t, this is going to decrease exponentially, so basically I don't care about it anymore. But when I'm at 1 over alpha t, right, and I want the smallest eta possible, because this term is increasing with eta. So the smallest eta possible for which this is small is O tilde of 1 over alpha t, in which case this thing is L squared over alpha t. Okay, so what I proved, I'm not going to do the formal proof because it's very simple and you just write what I wrote here. you will get this rate, exactly this rate, O tilde of L squared over alpha t. Compared to when you just have convexity, you get R0 L over square root t. Okay? So you get an improvement. This is a 1 over epsilon. Okay, 1 over epsilon rate. Okay, so we are happy because we said last time that already this quadratic improvement we would be very happy about. But we're not fully happy because this 1 over alpha can actually be pretty bad for machine learning application. Because remember, what is this alpha? This alpha is the amount of regularization that you put. But typically, alpha is going to be something like 1 over the number of examples that you have. So alpha is actually a very, very small number. Okay, so I'm going to write for you some examples of alpha, but alpha is typically a small number. So this is not such a great rate. It's also kind of disappointing because we get the gradient flow decreasing exponentially, and we're kind of shooting ourselves in the foot with this, bad discretization argument. So can we try to improve the discretization argument? And this is where smoothness comes in. Again, you remember, rate of convergence has to do with convexity or strong convexity. The regularity, the smoothness of the function comes in the discretization. Okay, so the smoothness part is not going to improve that part. It's not going to improve the gradient flow. It's going to improve the discretization part. Okay, so smoothness. So the definition of smoothness is just this. F is beta smooth if grad f, the gradient, is beta Lipschitz. Okay, which just means that the norm of grad f of x minus grad f of y is smaller than beta times the norm of x minus y. Okay, so examples are logistic regression, least squares, importantly not SVM. Okay, the hinge loss is not smooth. So what happens when you're beta smooth? So again, what we're going to try now to improve is the discretization argument. Okay, so intuitively, we want to improve the discretization argument. So what happens exactly? So you remember why did we get this eta L squared? This eta L squared, it came from a function like this, right? Where you're very close to the optimum, but the gradient is still of size 1. So if you make a step of size eta, then you're at distance eta from the optimum. Okay, so you get these big variance fluctuations. This is not going to happen with a smooth function. With a smooth function, at the optimum, the gradient is 0. Okay, so you can presumably make much bigger step. Maybe more concretely, with this inequality, what do you have? What do you have in particular? Note that the norm of grad f of x minus 1 over beta grad f of x. Okay, so if I do a step of gradient descent minus grad f of x, how much can that change? This is smaller than beta times, what do I get? Maybe I get minus some small constant. Or maybe let me put an eta here, sorry. This is smaller than beta, eta, norm of grad f of x. So if eta is some small constant over beta, what is the picture that I get? This is x. This is grad f of x. And I have a small ball here, and all the gradients, on this, from x to a gradient step, they are all in this small ball. Okay, all the other gradients are here. So they are all pointing, the vector field is not changing too much. They are all pointing in the same direction. Okay, so what this suggests very strongly, this suggests eta equals small constant over beta is fine for the discretization. Okay. If that is true, if you can take such a big eta, okay, imagine beta is a constant. We're now taking constant step size. Whereas before, here, we were taking very tiny step size. What is eta here? Eta is exactly R0 over L square root T. Okay, so in the non-smooth case, you need to take a very small step size, a step size which is decreasing with the total number of steps that you're going to make. Whereas in the smooth case, you can afford to make a big step size. This makes a dramatic difference. Okay, in practice, you want to always do that. You don't want to take this very tiny step size. You want to take a big step size. You know, you get this big gradient, you want to move. So what happens? Now we just need to plug in this eta into our formulas. Right? This formula for the gradient flow and that formula. So what are we going to get? So we get smooth, non-strongly convex. We get the following. We get R squared 0 over T times beta. That's the rate of gradient descent. So that, again, what is the algorithm here? It's just gradient descent with constant step size, 1 over 10 beta. That will be the rate of convergence. Now, what about smooth and strongly convex? So note, by the way, this is again 1 over epsilon. Okay, so again, we beat the 1 over epsilon squared. We improve. Now, what happens with smooth and strongly convex? Now we're going to be very happy because we just have the exponential term. So we get R squared 0 e to the minus alpha over beta t. Okay, which we rewrite. So it's useful to introduce the term kappa, which is beta over alpha, and this is called the condition number. Condition number. So this is a very important parameter. Okay, so the smoothness over the strong convexity, the smoothness over the curvature, and so this term is just R squared of 0, the distance at the origin, e to the minus t over kappa. Okay, so in terms of epsilon, this is really a kappa log 1 over epsilon rate. So you see, we're happy. Center of gravity was doing dimension times log 1 over epsilon, and now we see that gradient descent also does something times log 1 over epsilon, whereas this something is a condition number. Because the condition number is a sort of gradientish, it's a local dimension if you want. I don't know if that was a great term. But it kind of captures the idea. So if you're both smooth and strongly convex, you go very fast. You only need to do that many steps. All right. So I'm just going to write one formal inequality. I'm not going to prove those results. All of those results you can just check in my monographs, the actual step-by-step proof. But it's less, I think, useful than this derivation. Although the other ones are correct and this is not correct. So, what else did I want to say? The key point that I want to make is that you can actually do better than this. So this was a naive argument for discretization of a smooth gradient, a smooth vector field. So you can do better discretization argument than this, which is what I'm going to get at next. Okay, so next I'm going to tell you that when you have smoothness, you can actually be much more subtle than just doing a gradient descent. There are better algorithms. These algorithms, they go under the umbrella of acceleration. Okay, Nesterov's acceleration, Nemirovsky acceleration, that's what I'm going to explain. And you get another quadratic improvement. So this was a quadratic improvement over 1 over epsilon squared. We're going to get 1 over square root epsilon in this case, and we're going to get square root kappa in that case. Okay, and these are very, very good algorithms that really work well in practice. Okay, is there a question on what's written on the board right now? Yeah?
Yesterday you saying like we're doing this to see like if in practice we can still converge with like smaller number of iterations, but then how sensitive is this to like the choice of beta? Because I mean you have to guesstimate beta, right?
Yeah. So beta is not such a complicated parameter to estimate. So I'm gonna give you examples. Beta is really typically a constant. If you do logistic regression, beta is whatever, 2 or something. If you do least squares and your data is normalized, it is 1. Okay, so beta is not something difficult to estimate. Yeah. No other question on what you did so far? Okay, so the only inequality I want to write before we move to the actual lecture 4 is improvement that you get on a smooth function with gradient descent. So the improvement goes like this. Okay, so just one 4 mole inequality. Oh, this is not a great pen. Okay, so one 4 mole inequality. Here is the claim. If I look at the function value of, so I'm going to write x plus. From now on, it's one step of gradient descent with 1 over smoothness for the step size. X minus 1 over beta grad f of x. Okay, note it's exactly 1 over beta, not constant over beta. Okay, so now we're going to be formal, so you know, I'm going to get away with exactly 1 instead of the small constant over there. So here is a claim. The improvement that I get in function value on a smooth function from one step of gradient descent is upper bounded by minus 1 over 2 beta norm of grad f of x squared. Okay, so if my gradient is pretty large, then I get a sensible improvement in terms of the function value. Okay, so this is just a true inequality, very useful one. So let's do the proof. So first, here is a claim. I have the following inequality for a smooth function. F of x minus f of y is smaller than the gradient of f not at x but at y. Inner product with x minus y plus beta over 2 norm of x minus y squared. Okay, so the way I like to remember this inequality is that it's like the convexity inequality, except that instead of taking the gradient at x, we take it at y, and the price we pay for this is exactly this discrepancy. Okay. Note, for instance, if I apply this at y equals x star, right, this term would be 0. So of course you need some discrepancy. This inequality has nothing to do with convexity. It's not about convexity. It's just about smoothness. It's just for a smooth function. Okay, so the proof is super simple. I mean, there is only one thing you can do, which is to do Taylor's theorem. So f of x minus f of y, or even, it's not really, it's not, okay, just whatever. So this is just the integral from 0 to 1 of grad f of x plus, let me see, plus t times y minus x, inner product with y minus x dt. Okay, this is the time derivative of this function. Okay, and did I mess it up? Maybe I messed it up. I get at time 1, yeah, I messed it up, of course. X minus y. Yeah, x minus y. Yeah, okay. Y minus x. Okay, this is, okay, maybe this is correct, I think. because if I put another minus sign, then it changes the 0 and the 1. Okay, this is correct. This is a time derivative. This is minus the time derivative of that function. So it's that function at 0 minus that function at 1. That function at 0 is f of x. That function at 1 is f of y. Okay, good. So something is bugging me. Oh, yeah, that's good. So this is upper bounded by the integral by smoothness now of grad f of x, or maybe grad f of y, inner product x minus y, plus beta t times the norm of x minus y squared, dt. Okay, I just use the fact that this vector is in the ball centered at grad f of y and of radius beta times the norm of x minus y. Okay, so this part of the integral does not depend on t, and it's the integral between 0 and 1. So this is grad f of y, x minus y. And here I just get the integral of t dt, so between 0 and 1, so that's 1/2. Yeah. It's not t squared because I just use the smoothness between that point and that point, which is t times this. Yeah, I see. You guys wanted me to write this before. And that's a better thing to write. Okay. Yeah, thank you. So this is equal to grad f of y inner product with x minus y plus beta over 2 norm of x minus y squared. Because the only reason we did this is to get this 1/2, which is a nice thing to get. Okay, so now I claim that this inequality trivially follows from that. Let's just do it. So you see, if I just plug it in there, so what do I get? So let's say star, and this is double star. So double star implies the following. It implies that f of x plus minus f of x. Okay, this is smaller than grad f of x inner product with x plus minus x plus beta over 2 norm of x plus minus x squared. Which is what? This is minus 1 over beta, the norm of grad f of x squared. And this is plus beta over 2 norm of grad f of x squared. Okay, so this is minus 1 over, and there is a 1 over 2 beta. Right, because there is a beta square, 1 over beta squared that comes out. So minus 1 over 2 beta, norm of grad f of x squared. Okay, so using this inequality, you can very easily prove those statements that I wrote here in blue intuitively. Let me make another comment about this. So here is another comment. Let me see how I want to make it. Remark. This inequality, so double star or star, also shows that gradient descent on a bounded non-convex function finds a stationary point, an epsilon stationary point, in 1 over epsilon squared steps. So what is an epsilon stationary point? A stationary point is a point where the gradient is equal to 0. An epsilon stationary point is where the norm of the gradient is smaller than epsilon. Okay, why is that? As long as I'm getting through points which are not epsilon stationary point, I know that I must improve my function value by epsilon squared. So if I have a bounded function, I can do at most 1 over epsilon squared such steps, because every time I improve by epsilon squared. Okay, so this is pretty interesting. It's a result on non-convex functions, which is also something important. Yeah, proving optimality of this is highly non-trivial. Whether you can do better in small dimension remains an open problem. So you see, we very quickly touch on things that we don't know. Yeah?
So you said just bounded, not smooth, or does it also have to be smooth?
Yeah, smooth. Bounded and smooth, yeah. Bounded and smooth. Otherwise, you cannot apply this inequality. Yes, thank you. All right, so that's it for lecture 3. Is there any question? So now we're going to move to acceleration. Yeah?
So for a smooth convex function,
Yes?
is there any general relationship between beta and alpha?
No. So here is the right way to think about it. Alpha is a lower bound on the smallest eigenvalue of the Hessian. So you look at the Hessian, that tells you, the second order information of the function. Alpha is a lower bound on the smallest eigenvalue, and beta is an upper bound on the largest eigenvalue. So these two things can be widely unrelated. Maybe I do an example, just to set. Example, so least squares. F of x is 1/2 norm of ax minus b squared. Okay, so you can easily check that the Hessian of f of x, the gradient is just going to be A transpose times this, and so the Hessian is just A transpose times A. So the Hessian is A transpose times A. Maybe let me put a 1 over 2m. Okay, so this matrix is of size m rows and columns. Okay, so you have the feature vector AIs. Okay, so A is like A1 up to AM. These are the features vectors. Right? In Rob's class, this was the XIs. Okay? So this is 1 over m. Okay, which you can rewrite as 1 over m, the sum for I equals 1 to m of the AI transpose. Okay, so this is a sample covariance matrix. Sample covariance of the features. So alpha is lambda mean of this thing, 1 over m A transpose A, and beta is lambda max, the largest eigenvalue. So note that if the AIs are all normalized, have all L2 norm less than 1, then beta is less than 1. If the L2 norm of the AI is less than 1, then beta is less than 1. Okay, so smoothness is not a big deal. It's just about normalization. Okay, so that's why I said beta, you can really think about it as some constant number. Alpha, on the other end, is something much more tricky. The covariance, it's all about how well do I span every direction. So if there is some direction which is rarely visited, if there are some coordinates that I see rarely in my example, if I have a subpopulation which does not appear often, then my alpha is going to be very bad. Okay, so alpha can be very bad. And that's why this alpha, that's why in particular, typically you don't do this, you do ridge regression. So ridge regression is you do that plus a regularization term, exactly to combat the effect of the small subpopulations that can mess up your convergence rate. Okay? All right, so we have 20 minutes to do acceleration. Let's see. It's probably not going to work, but let's try it. So I'm just going to do Nemirovsky's acceleration, and then this afternoon we can do momentum and other stuff. Yeah, sure.
It seems like you have control over alpha using regularization.
Yeah.
Is there anything you can do about beta?
Just choose a better loss function, normalize your data better. I mean, there's no general trick, no. Actually, that's not exactly true. There is something you can do. You can do convolution. So one way to smooth a function is to, here is one formula that smooths things. F hat of x is just the expectation of f of x plus z, where z is some noise. Okay, some noise operator. So if you do that, and f was reasonably smooth, then f hat is going to be more smooth. Okay, so you can do stuff like that. In fact, yes, this is very useful in many, many cases. Maybe I make a comment now, actually. Yeah, but this question, this was a good question. So here is another thing that you can do, which I'm not going to touch on. So, but if you read paper about optimization, they make a big deal out of this, so you need to know about it. Sometimes f is non-smooth, but can be written as f is g plus r, where this guy is smooth, and that guy is simple. Okay, so sometimes you have non-smooth functions, but it's for a reason that you understand very well. So what is the typical example? Typically, r of x is the L1 norm of x. That's like the most famous example. So the L1 norm is non-smooth. It's convex, but non-smooth. But on the other hand, it's very simple. If you have an L1 norm in your objective, maybe you can do something else. You can take it apart, in some other way. So basically, everything I told you so far works exactly the same on functions like this, that can be written as some convex function, which is either smooth or strongly convex or whatever, plus some other function which is simple. What does simple mean? Simple means the same thing as when in the beginning I said that my convex body is going to be simple, meaning that I need to be able to do basically any operation that I want with this function r. For instance, I should be able to minimize it when I add a linear function. So typically, gradient descent, another way to view gradient descent is that you have your function, you linearize where you are right now, and you minimize this linearized version, subject to not moving too far. Now, what you want to do is that you want to say that this added non-smooth function r, you can also do that. You can minimize the linear function, the linearized version of g, plus this function, subject to not moving too far. If you can do that, and in the case of the L1 norm, there are closed form formulas to do that, then all the rates go through. Okay, so this is like getting into what's called structural optimization, exactly trying to go beyond this oracle model where you say, I have just this function that I can compute gradients. Maybe you have more structure to it. This is one such more structure. So in that case, people refer to, for instance, gradient descent as a proximal step algorithm. So these are just keywords if you want to look into the literature of those things. I don't want to touch into this. It gets just not pretty. So, okay. Any other question? Okay, so lecture 4. acceleration. So it turns out that 1 over square root epsilon for smooth, non-strongly convex, and square root kappa log 1 over epsilon for smooth, strongly convex are achievable. Okay, and you can prove lower bounds just in the same way as I proved that 1 over epsilon squared was a lower bound. You can prove that those are the best rates. Okay, and I don't have a very general philosophical way to tell you that, that these rates are achievable. It turns out they are, and I'm going to prove it. Okay. So what could, okay, so let's start. What could an optimal algorithm look like? So what could be a better algorithm than gradient descent? So basically, what's the problem of gradient descent is that it has no memory. But if you have a smooth vector field, you know that the vector field is not changing too much. So you can hope to reuse previous gradients. Okay, you shouldn't forget everything that you've done before. So what is the extreme of that? The extreme of that is I have computed all those gradients, and I'm in this oracle model where I can do any type of computation. Computational complexity is not really a problem for me. What I could try to do is that I could try to actually minimize my function on this entire subspace. Okay, so let's say crazy idea. Xt plus 1 could be something like the argmin over the span of all my previous gradients, grad f at x0, etc., up to grad f at xt, of my function f of x. Okay, I could try to bootstrap whatever algorithm I already have. Because this doesn't seem so, I don't know, it's not clear whether this is a good idea or not. Maybe it's very costly to do this, you know. But certainly this feels like the best you can hope for if you just use gradient information. This is a subspace where you know your function is varying. So, you know, maybe the rest doesn't matter. So it turns out if f is quadratic, okay, so what is this, by the way? This is of the form sum of lambda s grad f of xs. Right? It's some linear combination of my previous gradients. And the game is trying to find those coefficients. If f is quadratic, it turns out that lambda s has a closed form formula. Okay? Which is not too hard to compute. So this is one of the problem session. And this algorithm in this case is called conjugate gradient. Okay, so this is a very good algorithm for quadratic functions. It is just an instantiation of this general idea. Okay, and it turns out that you can do it for quadratic function, and you can even prove that it gets this rate square root kappa. Okay, so it does exactly what we were hoping to do. Now for general convex function, you know, I don't know what can happen. So what Nemirovsky, so conjugate gradient goes back to the 50s or 60s. When Nemirovsky came on the scene in, I guess, in the 70s, he started to work on this problem, and he managed to find an algorithm where you give just a specific formula for the lambda s, and it does, you know, as well as conjugate gradient descent. And the proof is very simple. So that's what I'm going to do now. All right, so Nemirovsky's acceleration. This is from 82, the published paper. So the idea goes like this. Let me write the algorithm. So what could you do? Let's say you pull out of your hat some formula for those lambda s. You could try, at the very least, what you can try to do is to try to optimize the function on this line. Okay? Just do a line search on this combination of previous gradients. But you also have gradient descent. Gradient descent is also a very reasonable idea. So let's try to get the best of gradient descent and this conjugate point. So that's what Nemirovsky did. Nemirovsky writes, takes the argmin over x in some plane, pt, of f of x, where pt is nothing but the span of xt plus and the sum for s equals 1 to t of lambda s grad f of xs. Okay, so I need to be able to do this two-dimensional plane search. For instance, I could use center of gravity. Okay, so this step by itself is like a subroutine where I need to use some other algorithm. But I know that I have very high precision algorithm for two-dimensional convex optimization like center of gravity. Okay, so we're just going to ignore how to solve this problem. Again, you can use center of gravity, and just worry about how many iterations do we need of this outer loop. Yeah? From the sky. So you will see. I will derive them. It's a formula.
Okay, but specific set of lambda. This is a two-dimensional space.
Yes, this is a two-dimensional space. So maybe eventually, I don't remember the formula. We're going to work it out. But lambda s is going to be something like s. Okay, to be precise. Lambda s is a number, which depends on s. Lambda 3 is going to be 3.2. Lambda 5 is going to be, 4.9. And there will be a formula. All right? Xt plus here.
Oh, okay.
Yeah. So that's like for the rest of the day. X plus is a step of gradient descent with step size 1 over the smoothness. Okay, so let's do the analysis. Okay, if I had done the formal analysis of smooth gradient descent, you would have seen that, so for smooth gradient descent, so non-smooth gradient descent, what do we analyze? We analyze the sum of the suboptimality gap, the sum of the delta s. Okay, delta s is f of xs minus f of x star. Good? For smooth gradient descent, you can view it as analyzing a sum of like S delta S, basically. Okay, so if you do the analysis, you can view it like this. I don't want to do this. But basically, what I'm going to write now comes from this inspiration. So what we're going to analyze is a weighted sum of the suboptimality gap, which is a sum of the lambda S delta S. Okay, I pose this as what I want to analyze. Please.
Clarifying question.
Yes.
Are you identifying the position x with the tangent space? Or where does the grad f lead? Is it formally a vector?
Yeah. This is an excellent question, really good question. But in this entire class, I'm identifying the primal and the dual space. So this is like, the transpose of that. Formally, this is like transpose. Right? Just it's a row vector, and the x is a column vector. So if I transpose a row vector, I get a column vector. This doesn't make much sense, from a functional perspective. But answering your question leads to mirror descent. Okay, so it's a great idea, but I don't want to get into it. Okay, so this is just a vector. Maybe more mundanely, this is a vector in Rn. Whether it's a row vector or a column vector, I don't make the distinction. But it's an excellent question. Okay. What am I going to do? All right. So I'm just going to upper bound this by convexity. This is smaller than the sum for s equals 1 to t of lambda s let's call it GS, or just grad f of s.
What is delta s again?
Delta s, these are the things that I try to be consistent about. Delta s is f of xs minus f of x star. Okay, it's just the suboptimality gap. Okay, I'm just, instead of analyzing the suboptimality at the end, I'm just analyzing a weighted suboptimality. Okay, so this is smaller than that inner product with xs minus x star. Now, first magic, note that grad f of xs is orthogonal to xs. Okay, just because I minimize on this subspace, so when I find a point, that point is in the subspace, and the gradient has to be orthogonal to it. Okay, so this is equal to the sum for s equals 1 to t of lambda s grad f of xs inner product with minus x star. Okay, because xs is in the plane ps minus 1, and grad f of xs is in the orthogonal of that plane. Right? If it had some component in the plane, then I could keep improving in the plane. Okay. So now I just use Cauchy-Schwarz, and what do I get? I get this is smaller than the norm of x star times the norm of the sum for s equals 1 to t of lambda s grad f of xs. Right? Now the point is, I know how to write this, the norm of this sum of gradients, because these gradients, they keep being orthogonal to the previous sum. Okay, that's because I minimize, on the span of the previous sum. So again, what did I just said? I just said that this is equal to the norm of x star times square root of the sum for s equals 1 to t of lambda s squared norm of grad f of xs squared. Okay, because grad f, say, at time t plus 1, is orthogonal to the sum of the lambda s grad f of xs. Okay, so I keep getting gradients which are orthogonal to the previous weighted sum. So every time I can peel them off when I get the square, I can just use Pythagoras theorem, right? Pythagorean theorem. But I have a smooth function. And I know that for a smooth function, the norm of the gradient is a lower bound on the improvement. So I'm going to have some kind of self-bounding property where I bound the sum of the suboptimality gap by something that depends on the sum of the suboptimality gap. By smoothness, what do I know? I know that the norm of grad f of x squared, grad f of xs squared, by smoothness, and by smoothness I mean inequality star, I know that this is a lower bound. This is a lower bound on the improvement. So namely exactly 2 beta times delta s plus 1 minus delta s. Okay, this is because xt plus 1 is better than xt plus. Okay, I get more out of Nemirovsky's algorithm. I get more than what I would get with gradient descent. With gradient descent, star over there tells me that the function value improvement of gradient descent is 1 over 2 beta, the norm of the gradient squared. So the norm of the 1 over 2 beta, maybe I put a 1 over 2 beta here to not confuse you further, right? And this is f of xs plus 1 minus f of xs. Yeah, I see why you're not happy. It's this. Okay, that improvement. It's delta s minus delta s plus 1. Right, so the difference in suboptimality gap, which is f of xs minus f of xs plus 1, is lower bounded by the norm of the gradient. That's smoothness. So I can continue my inequality there. And what do I get? I get that this is smaller than the norm of x star times square root. And what do I get? I get 2 beta, the sum for s equals 1 to t of lambda s squared delta s minus delta s plus 1. Okay, maybe I write it entirely. I get the sum of lambda s delta s is upper bounded like this. Okay, so that's basically the end. Now it's just like undergrad, I don't know in what course you see that, but discrete math. So you have this inequality, and you get to pick the lambda s, and you want to have a good upper bound on delta s. Not saying it's trivial, but it's not very hard. So let's just do it. But is it clear, this inequality? How I got there? Yeah, it's fine. So now I'm just going to do, you see that you always want to do the same thing. You want to do integration by parts. Right? You want to change this delta s minus delta s plus 1 into a delta s times a lambda s minus lambda s plus 1. Okay, so this is upper bounded by the norm of x star times square root of 2 beta, the sum for s equals 1 to t, of what? So I get delta s times lambda s squared minus lambda s minus 1 squared. Right, so the integration by parts would exactly tell me that this is equal to that plus something else. And this plus something else is non-negative. Okay? Non-positive, actually. It's negative. Okay, so you can ignore this plus term. I don't want to write it down. Right? Right? Just, okay. These two things are the same. And lambda s squared times delta s plus 1 is the same thing. If I shift the index of summation, it's the same thing as delta s times lambda s minus 1 squared. Okay, so I just have the first term and the last term, which should be there, and those terms do not matter. Good. So now I get to pick lambda s squared. So I'm just going to pick it so that I get everything that cancels. So now, pick lambda s such that what? 2 beta lambda s squared minus lambda s minus 1 squared is equal to lambda s. This is just a quadratic, formula. And you just work out lambda s as a function of lambda s minus 1. Okay, so this is like the 4.9 and 3.2 that I was talking about at the beginning. They come from this formula. But intuitively, you see what's happening. This is like, if I see lambda s as a function of s, it should be that the derivative of the square is like itself. Okay, so this is like lambda s should be, let me work it out. If I get s squared, okay, yeah, if I get s, then I get s squared minus s minus 1 squared, which is like s. Okay, but I get this 2 beta, so it's probably beta s, or s over beta. Yeah, if I get s over beta, then s squared over, like the 1 over beta squared cancel with the beta, so I have 1 over beta on the left side, 1 over beta on the right side, and I get s squared minus s minus 1 squared, which is like s. Okay, so lambda s is like s over beta. I wasn't too far off. And now what do I get? I get that this term over here is in fact equal to the norm of x star times the sum of lambda s delta s, square root, Okay, so I get the sum of lambda s delta s is bounded by x star times the square root of that sum. So I get that the sum of lambda s delta s is bounded by the norm of x star squared. The delta s are decreasing, okay, because I keep improving. So this thing is bigger than delta t, the gap at the end, times the sum of the lambda s. But the sum of the lambda s, it's like t squared. So this is like delta t, t squared over beta. So you get delta t is smaller than norm of x star squared times beta over t squared. Okay, again, I just use that the square root, I get the same term on two sides, so I can square and simplify. I get the sum of lambda s delta s is smaller than norm of x squared, but the sum of lambda s delta s is bigger than delta t because the delta s are decreasing, so it's bigger than delta t times the sum of lambda s. And the sum of lambda s, because each lambda s is like s, the sum of lambda s is like t squared. So I get that this term is like delta t, t squared over beta, and it's smaller than x star squared. So delta t is smaller than beta times the norm of x star squared over t squared. Okay, so in terms of epsilon, this is a 1 over square root epsilon algorithm. Okay, it's really amazing. And this is optimal. Okay, sorry that I went over time. Is there any quick question? Oh, it doesn't have to be so quick. Okay. Yeah?
Did you keep choosing your new gradients or orthogonal to all the previous ones? But like at some point you run out of dimensions. Like is there also some sort of like...
Oh, sure. I mean, yes. So eventually, so this algorithm is going to finish in at most n iterations. Yeah. In fact, this family of conjugate algorithms, they all finish in at most n iterations once they have exhausted all dimensions. But you should think these algorithms are for like the case where n is very large. Yeah. Okay, so this is really the shortest proof of acceleration. There is nothing simpler than that. This afternoon we'll do the momentum method. So momentum is a different idea that gets you the same result, but it's useful in other contexts. And we'll do variance reduction also. Yeah?
Why is it called acceleration?
Just because you go faster. It's 1 over t squared instead of 1 over t. Gradient descent is 1 over t, and yeah.
Maybe it's a silly question, but the span of x plus and the sum of this elimination will not change if you change the lambda, right? So
No, it would change. I mean, this is one direction, and this sum of lambda s is some other direction, and I search on this plane. Now, if I have a different lambda s, I have a different vector. So it's going to change the plane over which I'm searching. All right, thanks. Maybe. Yeah. Go ahead. I will. Thank you.